Welcome back, everyone. Last week we laid the groundwork. Binary storage, computer architecture, how machines think in ones and zeros. This week we're putting that foundation to work. We're going to get into the nuts and bolts of how computers actually store the kinds of materials you'll be working with every day as information professionals. Images, text, audio, and video. I want to be direct about something up front. The goal here is not to turn you into software engineers. It is to give you enough technical literacy that when a vendor hands you a spec sheet or when a systems team asks what format you want for a digitization project, you can hold your own in that conversation. You need to be able to ask the right questions and push back when necessary. This week's readings are chapters 3, 4, and 5 of Leggett's Digitization and Digital Archiving. If you haven't read them yet, I'd encourage you to do so before you tackle this week's coursework. Let's get into it. Here's the fundamental problem computers face with images. The real world is continuous. Step outside and look at a tree. The colors you see transition seamlessly. Infinite gradations of green, brown, light, and shadow. A computer cannot store that. Infinite data requires infinite storage, and storage is always finite. So computers do what they do best. They approximate. The unit of that approximation is the pixel, short for picture element. Every digital image you have ever looked at is a grid of pixels, each one a single solid color. The human brain fills in the gaps and reads it as a cohesive image. This is essentially the same principle as pointillism in painting. Georges Seurat's famous Sunday on the island of La Grande Jatte is built entirely from small dots of color. Up close, it looks like nothing. Step back, and your brain assembles a complete scene. Digital images work on the same trick. The historical milestone worth knowing. The first digital image was created in 1957 by Russell Kirsch. It was a grayscale scan of his infant son, captured at 176 by 176 pixels. Not exactly high definition, but it was the proof of concept that launched an entire field. When we talk about resolution, we're talking about pixel density. How many pixels are packed into a given space? The most common unit is ppi, pixels per inch. You'll also see dpi, dots per inch, but there's an important distinction. PPI refers to a digital image's pixel density, while DPI technically refers to a printer's output capability. When you're talking about digital preservation, PPI is the more precise and appropriate term. Higher resolution means more pixels, which means more detail and more data. A 2000 by 2000 pixel image of a mountain range will show individual trees that a 500 by 500 version of the same image cannot. But that higher resolution image is also 4 times larger. This is the core tension in archival scanning. You want enough resolution to capture everything that matters, without creating files so large they become impractical to store, retrieve, and serve to users. There is no universal right answer to the question of scanning resolution. It depends on the source material, the intended use, and your institutional storage capacity. That said, we'll look at specific recommendations from the Digital Library Federation later in this lecture when we get to text. Now, once you have a grid of pixels, each pixel needs to store a color value. That's done with bits, and the number of bits per pixel is what we call bit depth or color depth. 1 bit gives you 2 options, black or white. That's fine for simple line art or pure text documents, but it's useless for photographs. 8 bits gives you 256 possible colors, which was standard on early personal computers. Adequate for simple graphics, but nowhere near photorealistic. The standard most of you will work with in archival contexts is 24-bit color, also called true color. That's 8 bits each for red, green, and blue, allowing approximately 16 million possible colors. The human eye genuinely cannot distinguish between 24-bit color and reality, which is why it became the benchmark. There's also 32-bit, which adds an extra 8-bit channel for transparency, useful when you need a clear or see-through background in a graphic. One small but interesting detail about 16-bit color, also called high color. It allocates 5 bits to red, 6 bits to green, and 5 bits to blue. The extra bit goes to green because human eyes are more sensitive to green light than to the other primary colors. That one extra bit allows more shades of green, which improves perceived realism without increasing file size significantly. Here's where things get practically important for archivists. A 24-bit true color image at high resolution is a large file. Leggett's book gives a concrete example. One single image in the chapter takes up roughly 23,621 kilobytes of data, compared to about 68 kilobytes for the text of the same chapter. Images are expensive, storage-wise. Compression is how we address that. The idea is to store the same information using fewer bits by finding and removing redundancy. The classic example: instead of storing data for each of 100 consecutive black pixels individually, you store one instruction that says 100 black pixels. You've conveyed the same information in a fraction of the space. That example describes lossless compression. No information is discarded. The image that comes out of decompression is bit for bit identical to the original. This is what you want for your archival masters. Lossy compression goes further. It discards data the human eye is unlikely to notice. Subtle color variations, fine gradients, in exchange for dramatically smaller files. The trade-off is real. Every time you save a lossy compressed image, you lose a little more data. After enough cycles, degradation becomes visible. JPEG is the classic lossy format, and if you've ever seen a photograph that looks blurry and blocky in a weird way, you've seen JPEG compression artifacts. Compression ratio is the quantitative way to talk about this. A ratio of 1 to 10 means the compressed file is 1/10 the size of the original. Higher ratio means smaller file, but for lossy formats, it usually means more quality loss. The practical rule: lossless for anything you are archiving and want to preserve accurately, lossy for access copies and anything you are delivering to users online. Let me walk through the formats you actually need to know. There are dozens of image formats in existence, but a handful dominate archival practice. TIFF, Tagged Image File Format, is your workhorse for archival image storage. It is almost always used lossless. It captures enormous amounts of data, and it is the preferred format for image preservation by the Library of Congress. If you are digitizing photographs, maps, artwork, or any other visual materials for a repository, TIFF is your archival master format. The downside: TIFF files are large, and most web browsers cannot display them. They are storage files, not delivery files. JPEG is the format everyone has heard of, and it is genuinely useful, just not for archiving. JPEG uses lossy compression and is excellent for photographs on the web. It handles smooth color gradients well. It does not handle sharp edges, high contrast, or text well. Never use JPEG as your archival master for anything. PNG, Portable Network Graphics, is lossless and was designed to improve on GIF. It supports true color and is a solid choice for web delivery of images that need lossless compression. It cannot be animated the way GIFs can, but for most archival access purposes, that does not matter. GIF is limited to 256 colors, which makes it unsuitable for full-color photographs. Where it still earns its place is with simple graphics, line art, logos, and web content, where color depth is not critical. The GIF format is also notable for its interlacing feature. An image loads in stages from low to high resolution, which improves the user experience on slower connections. SVG is the odd one out on this list. All the other formats are raster graphics. They store images pixel by pixel. SVG stores images as mathematical descriptions of shapes. This means SVG files are infinitely scalable without any quality loss, which makes them ideal for logos, diagrams, and line art. The Library of Congress includes SVG among its preferred formats. If you scale a raster image up, it pixelates. An SVG looks crisp at any size. Let me be direct about the practical workflow here. You will almost always maintain two versions of your image files, an archival master and an access copy. The archival master is your TIFF. It is large, it is lossless, it lives in your preservation storage, and is what you fall back on if anything goes wrong. If a patron needs something corrected, if a format becomes obsolete and you need to migrate, you go back to the master. You never deliver the master directly to end users. The access copy is your JPEG or PNG. It is smaller, it loads quickly, it works in browsers. It is what your users actually interact with. If it degrades or gets corrupted, you regenerate it from the master. This two-file strategy is standard practice and should be built into your digitization workflows from day one. Trying to retrofit it after the fact is a headache nobody wants. Before we leave images, I want to dwell on something that is easy to underestimate: the danger of proprietary and native file formats. Native formats are file types that only work with specific software. Photoshop's .psd is a good example. If you have a collection of .psd files and you lose access to Photoshop, you have a problem. The data is technically there. You just cannot read it. This is not hypothetical. In 1985, Andy Warhol created digital artworks on an Amiga computer. The files were discovered in 2014, nearly 30 years later. They required reverse engineering obsolete software just to view. The images came back, but only because a team of skilled engineers put in significant effort. Most collections are not that lucky. Format obsolescence is a slow-moving crisis in digital preservation. The right response is to avoid proprietary formats for archival storage whenever possible, to use open, well-documented formats with broad software support, and to have a migration plan so that when formats do become obsolete, and they will, you can move your content forward without data loss. One last point on images before we move to text. Scanning does not always produce a perfect result. A century-old photograph may have faded, a document may have been captured with poor lighting. Post-capture editing can help. The key tool here is the histogram. Think of it as a bar chart showing the distribution of dark and light values in your image on a scale from 0, pure black, to 255, pure white. If your histogram shows that the image's lightest values stop at, say, 180, that means you have no true whites. Adjusting the white point to where your histogram actually ends will brighten the image without adding or destroying data. The critical constraint: edit in ways that preserve information. Adjusting levels is generally safe. Applying filters that permanently alter pixel data is not. And critically, your monitor must be calibrated. An uncalibrated monitor can display colors inaccurately, which means any color corrections you make based on what you see will be wrong. Color editing on an uncalibrated monitor is genuinely worse than not editing at all. Text in a digital archive falls into two fundamentally different categories, and confusing them will cause you real problems. The first is born digital text, documents that originated as electronic files, Word documents, emails, spreadsheets, PDFs, created digitally. These can be stored, searched, and retrieved immediately as text files without any additional processing. The second is digitized text, physical materials, handwritten letters, printed books, typed manuscripts, that have been converted to digital form by scanning or photography. Here is the catch. From the computer's perspective, a scan is an image. It is a picture of text, not text itself. The computer has no idea there are letters in that image unless you do something extra to make the text machine readable. That something extra is OCR, which we'll get to shortly. The workflow implications are significant. Born digital materials go directly into a text-based archival format. Digitized materials require an image capture workflow first, then OCR processing, Then quality review before you end up with searchable text. Budget time and resources accordingly. Every character you type is stored as a binary number. Unlike image color encoding, which follows a logical progression, character encoding is fundamentally arbitrary. Someone had to decide that the number 65 means capital A, and everyone else had to agree. The history of how that agreement was reached is messier than you might expect. By 1960, there were at least 60 different character encoding systems in use. IBM alone used 9 different ones across its own product line. If you have ever tried to open a text file and gotten garbage characters, you have experienced what happens when two systems use different encoding schemes. This was a widespread problem for decades. The first major standard to emerge was ASCII, the American Standard Code for Information Interchange. ASCII uses 7 bits per character, giving 128 possible values. That is enough to cover uppercase and lowercase English letters, digits, basic punctuation, and some control characters. It solved the immediate problem for English language computing. The limitation became apparent quickly. ASCII has no room for accented characters, much less for Arabic, Chinese, or any of the world's other writing systems. Extended ASCII expanded to 8 bits and 256 characters, adding some Western European accents, but that was still nowhere near sufficient. The real solution was Unicode, which uses 16 bits per character and supports over 65,000 characters, covering virtually every language and symbol system in use today. Unicode is backward compatible with ASCII. The first 256 code points are identical, which made adoption much smoother. For archivists, the practical takeaway is simple. Use Unicode-compatible formats for text storage and make sure your metadata and finding aids are also Unicode compliant. It is the universal standard, and there is no good reason to work with anything else for new materials. Here is something that trips up institutions more often than it should. The most common text format in Office environments is .docx, Microsoft Word's native format. It is everywhere. It handles formatting well, and it is a terrible archival format. The problem is not that .docx is bad software. The problem is that it is proprietary. It belongs to Microsoft, it is optimized for Microsoft Word, and while other programs can open it, full compatibility is never guaranteed. Older .doc files from Word 97 behave differently from newer .docs files. Files created in Word 2010 may look different in Word 2024. And if Microsoft ever stops supporting the format, or simply changes it significantly, your archived files are at risk. The broader principle is straightforward. Proprietary formats tie your collection to a commercial product. Open formats do not. For long-term archiving, always prefer formats that are openly documented, maintained by standards bodies, and can be read by multiple applications. Let me run through the formats that actually hold up for archiving. Plain text, .txt, maximum compatibility. Any program on any platform can read a plain text file. The limitation is obvious. No formatting, no bold, no italics, no tables, no images. For pure text content where formatting does not matter, raw transcriptions, metadata records, log files, plain text is unbeatable. Rich text format, .rtf, adds basic formatting capabilities, fonts, sizes, colors, while remaining widely compatible. Not as clean as plain text for long-term preservation, but a reasonable step up when some formatting is needed. Open document text, .odt. This is the format to reach for when you need full document formatting and want an archival grade option. ODT is an ISO international standard. It is the default format of LibreOffice and OpenOffice, both of which are free and open source. Microsoft Word can also open and save ODT files. The Library of Congress recommends it for text archiving. When a proprietary .docx needs to be preserved, converting it to ODT is a sound strategy. HTML is underappreciated as an archival format. It is plain text under the hood. It is human readable in any text editor, any browser can render it, and it can incorporate multimedia elements through links. It is particularly well suited for web content that originated in HTML and for collections you intend to make available online. The Library of Congress endorses it. XML gets its own separate treatment in a moment because its role is distinct from the other formats. PDFA1 is a specialized archival variant of the familiar PDF format, standardized by ISO. The key constraint is that it strips out features that can cause long-term problems: embedded video, audio, JavaScript, executable code, and encryption. The result is a format that will render identically regardless of when or where it is opened. Future software is required to be backward compatible with it. For archiving text documents that need to look exactly like their originals, financial records, legal documents, publications, PDFA1 is excellent. Students sometimes conflate these two because they look similar syntactically. Both use angle bracket tags. Both are widely used in digital archives, but they do completely different things. HTML is about presentation. When you write a web page, you use HTML tags to tell the browser how to display your content. The tag marks a paragraph. The tag makes text bold. The entire point of HTML is to control what the reader sees on screen. XML is about meaning. It does not tell a browser anything about how to display content. Instead, it describes what the content is. If you tag a piece of text as the author of a document, any software that understands your XML schema can extract all the authors from your collection automatically. If you tag publication dates, you can sort and search by date. XML is the backbone of metadata schemas and is why structured digital collections can be searched, aggregated, and reused in ways that unstructured collections cannot. One practical illustration: Dublin Core, the metadata standard used by many digital repositories, is commonly implemented in XML. When you create a metadata record with elements like title, creator, subject, and date, you are writing XML. The tags are what make your catalog machine-readable and interoperable with other institutions' catalogs. HTML and XML are not competitors. They serve different purposes and are often used together. A good working knowledge of both is genuinely useful for digital archivists. Let's talk about one of the most practically important technologies in digitization work: optical character recognition, or OCR. Here is the problem it solves. A scanned page is just an image. The computer stores it as a grid of colored pixels. It has no idea there are words on the page. A user searching your collection for Mississippi River will get 0 results from a scanned document, even if the phrase appears on every page, unless you have done something to extract the text. OCR software addresses this by analyzing the image, identifying regions that look like text, breaking them down into individual characters, and matching those character shapes against a database. The output is machine-readable text that can be indexed and searched just like born digital content. This sounds straightforward, but the accuracy is highly variable and depends on several factors. Let me give you the practical breakdown. Resolution matters enormously. For any document you intend to run through OCR, scan at 300 dots per inch minimum. Higher is better. At lower resolutions, individual characters start to blur together and the software makes more mistakes. Document condition matters. A clean, sharp printout on white paper will OCR with high accuracy, often above 99%. A water-damaged letter from 1887 with faded ink, coffee stains, and torn edges will give the software serious trouble. Human review is essential for historical materials. Bit depth matters too. For clean documents, 1 bit black and white is actually preferable because it forces everything to pure black or white, eliminating the ambiguity of gray pixels that the software might misidentify. For damaged documents with stains or spotting, 8-bit grayscale is better because it renders those imperfections as gray rather than black, making it easier for both humans and the OCR engine to distinguish actual characters from damage. One thing worth knowing, some libraries, including the Library of Congress, use volunteers to review and correct OCR output through crowdsourcing platforms. This acknowledges something important. OCR is never perfect, and there is no substitute for human judgment on difficult materials. For handwritten documents, standard OCR is not the right tool at all. Handwriting recognition uses a related but distinct technology called Intelligent Character Recognition, or ICR. It is harder, less accurate, and considerably more expensive to implement well. If your archive includes handwritten collections, factor that into your project planning. When you are scanning text for archival purposes, the Digital Library Federation Benchmark Working Group provides specific recommendations that are widely accepted in the field. For pure black and white text, or text combined with simple line drawings, scan at 600 dots per inch with 1-bit tone. The high resolution gives the OCR engine plenty of pixel data to work with. The 1-bit depth keeps the output clean and sharp. For grayscale images, text that is part of a photograph or illustration, or documents with tonal variation, use 300 dots per inch with 8-bit grayscale. The lower resolution is compensated by the richer tonal information. For color documents, 300 dots per inch with 24-bit true color. You want full color information for faithful reproduction. For the archival file format, TIFF is the recommendation across all three cases. For web delivery, TIFF does not work. Use JPEG for photographic content, PNG or GIF for text and graphics with sharp edges. PNG and GIF handle crisp color boundaries more cleanly than JPEG, which means digitized text will be more legible. Audio adds a dimension to digitization that text and images do not have. Time. A photograph is a static snapshot. A sound recording has to capture continuous change across a duration. In the physical world, sound is a pressure wave, continuous, analog. A violin string vibrates, pressure waves propagate through air, your eardrum moves. There is no discrete unit of one sound. It is all continuous variation. A computer cannot store that. What it can do is take a very large number of snapshots of the waveform at regular intervals and play them back fast enough that your brain fills in the gaps and hears continuous sound. This process is called sampling, and the rate at which samples are taken is the sampling rate, measured in kilohertz. The standard for commercial music, what you hear on CDs and most streaming platforms, is 44.1 kilohertz, meaning 44,100 samples per second. At that rate, audio reproduction is indistinguishable from reality for the human ear. The rule of thumb is that the sampling rate needs to be at least twice the highest frequency you want to capture, and human hearing tops out at around 20 kilohertz, so 44.1 kilohertz covers it comfortably. For speech-only recordings, oral histories, interviews, spoken word content, you can get away with much lower sampling rates, around 11 kilohertz, without noticeable quality loss. But for archival purposes, the Consortium of Academic and Research Libraries in Illinois, known as CARLI, recommends a minimum of 44 kilohertz and a preferred rate of 96 kilohertz. When in doubt, capture more data than you think you need. You can always deliver lower quality access copies from a high quality master. You cannot reconstruct data you never captured. Alongside the sampling rate, audio quality is determined by bit depth. How many bits are used to store each individual sample? The more bits, the more accurately the amplitude of the sound wave can be represented. 8-bit audio sounds thin and noisy. 16-bit is the recording industry standard, what you get on a commercial CD. 24-bit is CARLI's recommendation for archival recordings, and it is the right target for preservation work. The file size increase from 16 to 24 bits is real but manageable. The second dimension is channels. Mono audio uses a single channel, one microphone, one track of audio. Stereo uses two channels. capturing sound from different spatial directions and creating a sense of three-dimensional space when played back through headphones or two speakers. Stereo is twice the data of mono, which matters for storage planning. Professionally produced recordings, music, documentary film, broadcast content are typically stereo. Older recordings, cassette tapes, vinyl records, dictation recordings, many of these are mono. When you are digitizing analog materials, match the channel configuration of the original. Do not upmix a mono recording to stereo. You are not adding information, you are just duplicating one channel and creating a larger file with no added value. WAV and BWF waveform audio file format, or WAV, is your primary archival audio format. It is the basis of the Library of Congress's preferred preservation formats, specifically the PCM wave format, where audio is encoded using pulse code modulation, is the gold standard. The broadcast wave format, or BWF, is a WAV variant that adds metadata fields specifically designed for broadcast use, including timestamps and provenance information. Use WAV or BWF for your archival masters. Apple's AIFF format is functionally interchangeable with WAV for most purposes. Most audio editing software handles both. AIFF is proprietary, but so widely adopted that compatibility is not a practical concern. If your source materials are in AIFF, there is no strong reason to convert them for archival storage. ASCII, free lossless audio codec, is non-proprietary, lossless, and produces files significantly smaller than uncompressed WAV. It is an excellent archival format, and the strongest argument for it is that it is open source with no licensing constraints. The limitation is that adoption has been slower than MP3 or AAC, and some older playback systems do not support it. If your institution uses software that handles FLAC well, it is worth serious consideration. MP3 is the world's most recognized audio format, and it is genuinely not appropriate as an archival format. MP3 uses lossy compression that works by removing audio frequencies the human ear is statistically unlikely to notice. The result is a file that sounds good enough for casual listening, but has had real data permanently discarded. Do not archive in MP3. Do deliver in MP3. It is ubiquitous, your patrons already have software to play it, and the smaller files are faster to download. MIDI is in a category by itself. It is not an audio recording at all. It is a set of instructions, essentially digital sheet music, that tells a synthesizer which notes to play and when. MIDI files are tiny because they contain no actual audio data. They were widely used in early video games and software, and if your archive includes old software or early digital music, you may encounter them. The catch: how a MIDI file sounds depends entirely on the quality of the synthesizer rendering it. The same MIDI file can sound radically different on different systems. Video is, at its core, a combination of everything we have already discussed. It is a sequence of still images, frames, played back fast enough to create the illusion of motion with synchronized audio. The standard frame rate for video is 30 frames per second. Every second of video you watch is actually 30 still images shown in rapid succession. Your visual system blends them into perceived motion. Film traditionally used 24 frames per second, which gives it a slightly different visual texture that cinematographers sometimes prefer. Keeping track of 30 frames per second across a feature-length recording requires a precise labeling system. That is what a timecode provides. A unique identifier for every frame that allows editors to synchronize audio and video tracks, make precise cuts, and reference specific moments in the recording. Like audio, video can be compressed using software called a codec, short for compressor-decompressor. Most video codecs are lossy. The MPEG-2 codec, for example, achieves compression partly by dropping frames that are nearly identical to adjacent frames. If nothing changes between frame 14 and frame 15, why store both? Lossless video codecs, Hofiof, Lagarith, JPEG 2000 exist and are preferable for archiving, but they produce much larger files. When you are digitizing video materials, there are four main decisions to make. First, resolution. Standard definition television is 640 by 480 pixels. High definition is 1920 by 1080. For archival digitization, you want to capture at the highest resolution the source material supports. There is no benefit to scanning a VHS tape at 4K resolution. The tape itself only contains standard definition information. But if you are digitizing a high-quality film source, capture at the highest resolution available. Second, aspect ratio. This is the width to height proportion of the frame. Older television used a 4:3 ratio. Modern widescreen uses 16:9. Films for theatrical release often use wider ratios still. The key principle: preserve the original aspect ratio. Cropping to fit a different display format is a permanent loss of information. If you have ever bought a movie in widescreen versus full screen format, you have seen this trade-off firsthand. Third, bit depth. Carly recommends 30-bit sampling for video. More bits per sample means more color information per frame. Fourth, scanning method. Analog video, VHS, Betamax broadcast tape is typically recorded using interlaced scanning, where each frame actually captures alternating horizontal lines. When digitized, interlaced footage can produce blurring artifacts from slight movement between fields. Progressive scanning, which is what most digital cameras use, captures the complete frame at once. For archiving, progressive is superior. If you are digitizing interlaced analog materials, look into deinterlacing as part of your processing workflow. Video formats are frankly more complicated than image or audio formats. There are many of them, most are proprietary, and the landscape changes faster than archival standards can keep up with. Here is the practical summary. Motion JPEG. 2000 is the closest thing to a gold standard for archival video. It is an open international standard. It uses lossless compression, and it compresses each frame individually rather than exploiting similarities between adjacent frames. This is important for archives because it means any individual frame can be accessed without decoding the entire file. It is the format used for digital cinema distribution. If you are building a video preservation program from scratch, this is where to start. AVI from Microsoft and QuickTime MOV from Apple are both proprietary and widely used. Carly acknowledges them as reasonable alternative options when Motion JPEG 2000 is not practical. They have broad software support, and if you are inheriting a large existing collection in these formats, migration to Motion JPEG 2000 is a long-term goal rather than an immediate requirement. MPEG-2 and MPEG-4. These are delivery formats, not archival formats. MPEG-2 is standard for DVDs. MPEG-4 is widely used for online video. Both are lossy. Both are excellent for making your collection accessible to users. Neither should be your preservation master. We have now covered this across 3 different media types, and the pattern is consistent enough that it is worth stating as a clear principle you can carry with you. For archival storage, always prefer lossless, TIFF for images, WAV or FLAC for audio, Motion JPEG 2000 for video. These formats preserve all the data, they are large, and they are your insurance policy. For patron access and online delivery, lossy formats are appropriate and often necessary. JPEG for images, MP3 for audio, MPEG-4 for video. These are smaller, faster to deliver, and compatible with the software your users already have. The practical implementation is a dual-file strategy. Maintain a lossless archival master and generate lossy access copies from it. The access copies are disposable. If they are lost or corrupted, you regenerate from the master. Never let the access copy become your only copy. This principle will come up again and again throughout your careers. Burn it in. Let me pull the key threads together before we close. For images, pixels, resolution, color depth, and compression are the four variables you are managing. TIFF is your archival master format. JPEG and PNG are your delivery formats. Avoid proprietary native formats for long-term storage, and have a format migration plan. For text, the shift from ASCII to Unicode resolved decades of encoding incompatibility. Avoid proprietary formats like .docx for archival storage. Prefer ODT, PDF/A-1, HTML, or XML, depending on the use case. When text is scanned rather than born digital, OCR is your bridge to searchability, but it requires clean scans and human review for accuracy. For audio, sampling rate and bit depth determine quality. 44 kHz minimum sampling, 24-bit depth, WAV or FLAC for archiving, MP3 for delivery. Match the original channel configuration when digitizing analog materials. For video, it is frames plus audio, progressive scanning, and lossless codecs for archiving. Motion JPEG 2000 is the preferred format. Make decisions on resolution and aspect ratio before you digitize, not after. The unifying lesson: lossless for storage, lossy for access. Maintain both.